In this video, we're going to take a look at constructing a neural network classifier that takes in some inputs related to gas and liquid flow rates and pipe diameters, pressures, temperatures, and pipe inclinations. Those are my input features, and it predicts what is the flow pattern associated with those inputs. So this is a classification problem. And for vertical flow, for example, we can have multiple different kinds of flow patterns. We can have bubble flow, we can have slug flow, churn flow, annular flow, and for horizontal flow, we also have the corresponding patterns as well. Uh, I do want to point out that in this specific example, the data set was acquired from this paper down over here, which was published in 2012, and it's a study from the University of Tulsa, and it really compiles data from several different studies ranging from 1982 all the way to 2007. And largely, we are looking at gas liquid flow for various inclinations, for various pipe internal diameters, densities of the liquid, viscosities of the liquid, and pressures and temperatures. And we also have the corresponding flow patterns associated with those conditions. And the flow patterns have been labeled accordingly. So the label 1 refers to dispersed bubble flow, label 2 is stratified smooth, and so on and so forth. So first things first, we are going to be reading in our data set. Uh, we are going to be solving this problem using a neural network classifier. And my data set is in a CSV file. I'm going to read that CSV file, and we can also look at what the data contains. You can see that I have readings of pressure, density of the liquid phase, density of the gas phase, viscosity of the liquid, viscosity of the gas, then the roughness, the pipe ID, angle, then the superficial liquid velocity and the superficial gas velocity and the associated flow pattern. So we want to see how many uh, data points are associated with any given specific flow pattern. So we want to be looking at the column labeled flow pattern. And we want to see how many counts are associated with each one of them. So when we do that, we can see that pattern 5 has close to 2,900 points, while pattern 1 only has 595 points, and pattern 7 has 125 points. And so looking at this data set, you can see that this is an imbalanced data set. There are several points associated with labels 5 and label 4, and fewer points associated with label 3 and 1, and very small number of data points associated with flow patterns 2 and flow patterns 7. Uh, but in any case, let's just go ahead and see all the features side by side and see what we can gather from that data, from the data. So I'm just going to use the um, pandas plot command. I'm going to be using subplots for each one of the column names. And I'm going to be uh, creating a figure of size 12 inches by 15 inches, and I'm going to show this. So now we have each one of the inputs. I have the pressure, I have the density of the liquid, density of the gas, viscosity of the liquid, of the gas, the roughness, the pipe ID, the angle, whether it's horizontal, vertical, or something in between, then the superficial liquid velocity, superficial gas velocity, and the flow patterns associated with them. And you can see that there are very few flow patterns associated with flow pattern 7 and very few associated with some of the others, but you can see that 5 and 4 are pretty much um, the most common patterns. And this is not the best way of looking at flow patterns, but this is a nice way of looking at all of the input variables in conjunction. An important thing to point out over here is that the density of the liquid, the gas phase, and the viscosity of the liquid and the gas do not change across this entire study. And that has implications for how we conduct our classification. All right, we're first going to look at creating a matrix scatter plot using the variables pressure, then the angle, the superficial liquid velocity, and the superficial gas velocity. I'm going to be using uh, the Seaborn pair plot command using the data frame uh, data, and I'm going to plot pressure. Then I have the angle. Then I have the superficial liquid velocity, and I have the superficial gas velocity. And I'm also going to color these points by the associated flow pattern, just so that it gives you an idea of what the problem entails. Uh, and I forgot to use the plt.show command, and that's why our plot didn't show up. And there we go. So what we have here is, I thought I also put matplotlib inline. Okay, there it is. Okay, I do have my flow patterns uh, over here. I have the different input variables. I have pressure, I have the inclination angle, I have the superficial liquid velocity, superficial gas velocity, and so on and so forth. So let me just make sure that I did this correctly. There we go. This is much better looking. All right. So now I have all of the variables that I wanted, and the points are colored by the associated flow pattern. You can see there's flow pattern 1, 2, 3, 4, 5, and 7. And what we can gather from this data set is that, yes, there are a few points that don't seem to belong. We'll address them in a later discussion. But for right now, you can see that there is no way of constructing a linear decision boundary that separates out the blue points from the orange points, from the green points, red points, and purple points, and things like that. This is actually a fairly challenging problem on the face of it, because we have 10 different inputs, and even just looking at it with 4 dimensions, it seems like a very challenging problem. Let's look at the most frequent classes. So for the most frequent classes, if I recall correctly, the most frequent classes were class 5 and class 4. So let's select those. I'm going to select, make sure that I select the flow pattern equal to class 4, or flow pattern equal to class 5. And again, I'm going to color the points. And when I color the points, we'll see the most frequent labels within our data set. So I did not match the parentheses, and that's a common mistake that I make. I should be a little bit more careful about doing this. All right. So we're going to be looking at just flow pattern 4 and flow pattern 5. And again, just with these two flow patterns, you can see that on a plot of pressure versus, say, superficial gas velocity, there's quite a bit of overlap between the points. And there's quite a bit of overlap, even if you were to view it with another axis, which is pressure versus superficial liquid velocity. And it's very hard to separate out these points visually. Which means that if you were attempting to fit a linear classifier that would separate out these points based on the inputs of pressure, inclination angle, superficial liquid velocity, and superficial gas velocity, it would be virtually impossible. Okay, so let's go ahead and think about how we can set up this machine learning problem. For that, we first need to create a data frame containing our input features. Our input features are going to be all of the variables within the data set. It's going to be the uh, pressure, and it's going to be the I'm just going to scroll up a little bit just so that I refresh my memory. We have the density of liquid, density of gas, viscosity of liquid, viscosity of gas, roughness, ID, VSL, superficial gas velocity. Okay. So we have the density of liquid, and we have the density of gas. We have the viscosity of the liquid phase. We have the viscosity of the gas phase. Then we have the surface roughness. We have the pipe ID, and we have the superficial liquid velocity. And we have the superficial gas velocity. Those are my inputs. And in case I did make a mistake, then it's going to let me know pretty shortly. And our target variable is the flow pattern. All right, so I have 1, 2, 3, 4, 5, 6, 7, 8, and 9 inputs. I'm think there should be 10 inputs. I'm missing the angle. So the angle, and just to be consistent with the ordering over here, I'm going to put the angle in between the pipe ID and the superficial liquid velocity. So the angle goes here. All right. So we did that. And first things first, we're going to be using a training and a test split. I'm going to be using a test size of 20%, which means that my training set is 80% of the data. I'm going to be doing something called a stratified split, which we haven't discussed yet. And we'll be discussing this in another lecture or two. But the basic idea is that you want your training data set to contain the same proportion of each of the labels as the test data set, and you want them in turn to contain the same proportion of labels as the entire data set. What do I mean by that? If I scroll up a little bit more, we can see that 5 and 4 are the most frequent classes. 3, 1, 2, and 7 are relatively infrequent. So if I were to choose a test data set, without taking into account the proportions of these various labels, it's entirely possible that my test data set, which is 20% of the data, might only have flow patterns 5 and 4 because I'm just randomly selecting 20% of the data set, and pattern 5 and pattern 4 happen to be the most frequent. I end up with a test data set that contains only those patterns. But if I use a stratified split, then I'm going to ensure that I select a training set that has the patterns or the labels in the same proportion as these numbers. And the test data set consequently will have labels, the distribution of the labels in proportion to what was contained in the original data set. So that's why I'm doing a stratified split. And we're of course going to be scaling our inputs, and we haven't talked about that yet. And finally, once we are done with all of this, then we need to construct our neural network model and specify its architecture. In this specific case, we're going to be using MLP classifier. We're going to be using 3 neurons each in 2 successive hidden layers. So for that, what we're going to be doing is we're going to be defining a model. Let's call it MLP, and that uses the scikit library classifier, MLP classifier, and we have hidden layer sizes. I'm going to have 3 in the first layer, so it's going to be 3, and then 3 hidden neurons in the second layer. And I'm going to be using an activation function that is the ReLU activation function. And again, I'm just going to fix the random state to be some integer. And I'm going to, the reason why is because I want the weights to be initialized from the same values every single time I run this Jupyter notebook, so I get exactly the same result. Now that I've defined this model, I need to train this model, which means that I need to fit it to my training data set. And that can be accomplished with the .fit command. I fit this to my training data set. And run the cell. And there we go, we're finished training, but we don't know how well this model is going to do. So we apply it against the holdout test data set. And for that, what we need to do is we need to define a new variable. Let's call that the predicted label. And that's going to be using the model MLP. And we're going to make predictions on my test features. And we're going to compare or rather, we're going to report the accuracy of those predictions. We're going to compare what was in my test data set with what is being predicted. And I'm going to report the accuracy of this specific classifier. So I'm going to call it test accuracy. And we are going to report the variable accuracy, and we're going to multiply it with 100 just so that we deal with percentages. And I'm only going to report it to 2 decimal places of precision and add a percentage label to that. All right, so I need to close out the brackets, squiggly brackets, and this is going to give me my test accuracy. And oh, I made a mistake. Accuracy is equal to accuracy score, which is what we use from sklearn. And we get an accuracy of about 70%. And this is not a great accuracy, and that's because we're using a model that's not so complex. And there's a reason why I'm doing this. But let's if we change the model complexity, perhaps we can get a slightly better accuracy. But I also want to be looking at my confusion matrix. So I'm also going to be importing my confusion matrix from sklearn, and I haven't done that yet. So what I'm going to do is I'm going to say from sklearn metrics, I'm going to import my confusion matrix display. And I'm going to display my confusion matrix based on the predictions. And I have my test data set. And I have my test labels and I have my predicted labels. And this is going to give me the confusion matrix. And this is my confusion matrix. So looking at this confusion matrix, I have my true labels on one axis of the matrix, and they have the predicted labels. And you can see that when the true label was a value of 1, it got it right quite a few times, but then it also misclassified it as label 5 quite a few times. On the other hand, when the true label was a value of 4, it misclassified it as label 3 a few times, got it right about 139 times, and misclassified it as label 5 about 40 times. So this is my confusion matrix, and clearly you can see that there are quite a few off-diagonal terms, which means that there are quite a few uh, misclassified test data points, which has contributed to this relatively low accuracy. And that's fine because we can always increase the complexity of the neural network and get slightly better accuracies and test predictions. And we'll see that in a bit. Okay, but more importantly, I wanted to show you what the weights look like going from the 10 different inputs to the 3 neurons in the first hidden layer. And you can look at that by just using this command MLP coefficients, and MLP is my model and coefficients are over here. And this is a lot of information, but essentially if we look at this array over here, you can see that I have 3 numbers. This denotes the weights going to the 3 hidden neurons from the first input. Then I have the weights going to the 3 hidden neurons from the second input. Then I have the weights going to to the 3 hidden neurons from the third input, all the way down to the weights to the 3 hidden neurons from the 10th input. And here I have the weights going from the 3 hidden neurons in the first layer to the 3 hidden neurons in the second layer. And then I have the weights going from the 3 hidden neurons in the second layer to the 6 output classes, or the 6 output nodes. And these represent the weights going to the output nodes. But I'm only interested in um, what's happening from the input nodes to the first layer. So what I'm going to do is just focus on that alone. So we're only going to look at the first instance of the weights. Let's just say that I'm going to call this weights um, from the input layer. And that's going to be these numbers. It's going to be these sets of numbers. I have 10 inputs and I have 3 hidden neurons. So I'm going to have um, 3 weights going from each one of the input nodes for a total of 30 weights. And it's kind of hard to visualize what's happening over here. It's best to plot the weights so that we actually see what these weights represent. So I'm probably going to just use, uh, let me figure size, maybe about 10 by 9. And I'm going to be using the seaborne heat map to represent the values of the weights. So I have the weights from the input. I'm going to be using a red and blue um, color map just to highlight the low and the high values. I'm also going to make sure that I put the numbers on the heat map. And I'm going to choose a minimum value of, say, -1. Uh, we'll try it with minimum value of -1 and maximum value of +1 and see what we get. This should work, except that I need to change this into a code cell. And I need to say blb.show. And there we go. So to read this one, I have the weights coming from my 10 different inputs numbered from 0 to 9. So those are my 10 different inputs. And then I have my hidden neurons, 0, 1, and 2. Hidden neuron 0, hidden neuron 1, and hidden neuron 2. And the weights going from the first input to the hidden neurons are these numbers, and the boxes are colored accordingly. And the weights going from, say, the ninth input to the hidden neurons are 0.37, 0.86, and negative 1.8. And the reason why I'm showing this heat map is to illustrate what's happening or how did the neural network interpret this data. You can see, look at the magnitude of the weights. You can see that the weights associated with the 0th input are relatively high. On the other hand, if you look at the inputs associated with, or the weights associated with input 1, we're looking at very small values, 10 to the negative 80, 10 to the negative 27. And likewise for input number 2, we're looking at very small weights. For input number 3, we're looking at very small weights again. Input 4 as well, and input 5 as well. And so what the neural network is essentially saying is that uh, the most important inputs or features that enabled me to make this classification are input feature 0, input feature 6, 7, 8, and 9. And this may seem a little bit counterintuitive because the neural network is essentially saying that these 5 input features going from 1, 2, 3, 4, and 5 are uh, pretty much meaningless for this classification. And this might seem counterintuitive, but if you actually look at the data, you will see why this is indeed the case. So let's scroll back up through our Jupyter notebook and look at the initial plot over here. So I have pressure, which is my 0th variable. I have density of the liquid, which is the first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth for a total of 10 inputs. And if you look at the input feature 1, input feature 2, 3, 4, and 5, they essentially have no variations whatsoever. For every single flow pattern, they have exactly the same value of the density of liquid, density of gas, viscosity of liquid, viscosity of gas, and the surface roughness, which essentially means that none of these inputs are useful for the classification. And that's essentially what the neural network is detecting automatically by working on your training data set. and it comes up with these weights, which essentially tell us that the input 1, 2, 3, 4, and 5 are meaningless inputs. So while we did use a somewhat complex neural network to get to this stage, it had three hidden neurons in the first layer and three hidden neurons in the second layer. And it's hard to interpret what's happening when you get to many hidden layers and many hidden neurons in each layer. There is still some information we can gather from the architecture of the neural network. Looking at the coefficients is one way of interpreting what the neural network is seeing. Now, the next question is, can I improve the performance of this neural network? Yes, perhaps, and I don't know in which direction we should go, but perhaps let's try something like maybe 10 neurons in the first layer, 10 neurons in the second layer, and let me start up 10 neurons in the third layer as well, and fit this to my training data set and test it. And I'm going to get a slightly better accuracy, and you can see that the accuracy went up to 85%, and my confusion matrix looks slightly different with a predominantly diagonal set of terms and less weight on the off diagonal terms. It's not perfect, but it's definitely an improvement over what we did previously. And so you can progressively change the complexity of the network and perhaps get better uh, results. The other thing I want to point out is that if um, the weights of the network indicate that there are some inputs which are relatively unimportant, then you can pretty much rerun this entire classification with just the input feature 0, input feature 6, 7, 8, and 9, and you don't need all of the 10 inputs. And that stands to reason in this specific data set. So that brings me to the end of this discussion where we illustrated how to use a neural network to predict the labels associated with multiphase flow. Specifically, we were looking at predicting the flow patterns given the pressures and the temperatures and the pipe ID and the superficial liquid and gas velocities and the fluid properties.